Assalamu alaikum. This is Talha bin Nadeem, and today we will start off with a new topic of combustion and combustion chambers. In the last lectures, we have already completed the topics of carburetor and mechanical injection system. Now we will start off the new topic, and that is of the combustion and combustion chambers. So I will give you the brief introduction about this topic. We will discuss the combustion in SI engine and CI engine in quite details, and we will also have a brief overview regarding the combustion chambers which are being incorporated in SI and CI engines. So our major focus will be on the combustions, and we will have a brief discussion regarding the combustion chambers as well. So now moving forward, I'm starting off with a definition of a combustion. So what is combustion? We have been studying the definition of we have been studying the combustion process since maybe like from the ninth grade. The combustion is basically a chemical process. Is a burning of a, we can say it is a burning of a fuel in the presence of oxygen. So and as a result we basically get carbon dioxide and hydrogen water vapors as a molecules as a combustion products. So uh, combustion is a chemical reaction in which certain element, so by the word certain element here it means that the fuel uh, like hydrogen and carbon combine with oxygen, liberating heat energy and causing an increase in the temperature of the gas. So we would not only after the combustion the energy is being generated, but the temperature has also rise, and this is what is happening inside the combustion chamber when we combust the air fuel mixture. Combustion reactions and equations. So as I mentioned earlier, that when we combust a fuel, we basically, what happens is we basically get carbon dioxide and water vapors as a combustion products, and excessive amount of energy is being released, which is being utilized, which is being converted into the useful work. um, the products of the combustion reaction include carbon dioxide and water vapors, as I mentioned earlier. The reaction typically gives off heat and light as well. We do not use this light component, but we basically utilizes this heat component in the IC engines, and we produce some useful work to if I'm talking about an automobile, then we are basically running an automobile uh, with the help of this, by utilizing this heat, by converting this heat energy into some useful work. The general equation of the combustion reactions can be written as when fuel is combined with the oxygen, it is converted into carbon dioxide and water. The burning of a here I have given an example that, for example, when you burn a charcoal, it is a combustion reaction, and for example, when you in your home, you can see that you have a stove where you cook your meals. So what you do is you basically uh, you basically burn the sui gas which is coming in your houses, and that is also the example of a combustion reaction. So the reactions, the general reaction would remain same, and it would be in the form of, for example, if I am talking about a methane, which is CH4 plus O2, and as a result I will get carbon dioxide and water vapors. So if I balance this equation, I will add 2 here, and I will add 2 here as well. So this will be the combustion equation for the burning of methane gas. Moving forward, next we have the different we have the calorific value. So different fuels have different calorific value, and not only that, different fuels have different calorific value. We have two different types of a caloric value. First one is the net calorific heat value, and the second one is gross calorific heat value. So the question is, what is the difference between these heat values? uh, what is net calorific heat value and what is the gross calorific heat value? So the difference is quite simple, that when, as I mentioned earlier, that when we are combusting a fuel, here you can see that we have this water component, water molecule, water vapors as well, which are being produced as a result of a combustion. So when these water molecules are remained in the vapor form, and these water vapors are converted into the vapor by absorbing some heat, so some useful amount of the energy which could have been converted into the useful work is being utilized in converting this water into the water vapors. So this is the amount of energy which we are not using, and we are releasing it in the exhaust. So if we are not utilizing this energy, and we are exhausting, we are releasing these water vapors in the atmosphere, in the exhaust of your IC engine, then this calorific value will be called net calorific value. Means we have not utilized the energy which is being stored in converting the water from liquid to water vapors. So remains in the form of a vapor. These calorific values are called net calorific value. Whereas if we are talking about gross calorific value, in this gross calorific value, we have utilized the exhaust of the IC engine to that much extent that this water vapors have started to condense, and we are utilizing that energy which was stored, which was utilized in converting the water into the water vapors. So this is the main difference between net calorific value and gross calorific value. So in the gross calorific value, we are utilizing the exhaust up to that point that the water vapors will start condensing. So we can conclude it by saying that gross calorific values are greater than net calorific value, because we are utilizing as much amount of the energy which we can utilize in the useful work. Now moving forward, next we will discuss the homogeneous mixture and some of the heterogeneous mixtures, and some heterogeneous mixture. Starting off with the homogeneous mixture, when we are talking about the IC engine, as we have already studied that carburetor is that equipment which is preparing the air fuel mixture, desirable air fuel mixture for the IC engine, and that air fuel mixture would be nearly homogeneous mixture. So and in a homogeneous mixture which is formed outside the cylinder. In SI engines, the mixture is formed outside the cylinder. The fuel and the oxygen molecules are more or less uniformly distributed, but there are some disadvantages of carburetor which we studied, which I have explained in the last lecture of the mechanical injection system topic. So I explained the why injection systems are being incorporated, and one of the factor was that it carburetor does not ensure that uniform in when we have a multi-cylinder engine, we have a uniformly distributed air fuel mixture, but somewhat it it is giving a uniformly distributed mixture. So the combustion is initiated inside the cylinder at a particular instant towards the end of the compression stroke. So when we have compressed the air fuel mixture and the piston has reached the top dead center, the spark plug will ignite this air fuel mixture and combustion will take place. We will discuss the details that how this combustion has initiated and how it has been propagated throughout the combustion chamber, and what are the stages of the combustion in SI engine. We will discuss all these things in this video lecture in the later slides. Once this fuel air mixture is ignited, now the flame front appears. The flame has just appeared, and now it will rapidly spread throughout the combustion chamber. For example, we have the top. This is the cylinder head, and here is the spark plug. It is igniting the air fuel mixture. So the fuel which is closer to this cylinder head will first ignite, and then the flame will appear only in the upper layers, which is basically called quiescent zone. I will explain this where this quiescent zone exists. So in this quiescent zone, the flame will appear, and this flame will rapidly propagate throughout the combustion chamber. This is what is happening when we are talking about the combustion in SI engine. So this flame will rapidly spread throughout the combustion chamber. the flame propagation, the question is that how this flame is propagating. So we have basically two factors on which this flame propagation depends. Number one is the heat transfer between the already combusted fuel and uncombusted fuel. The second one is the diffusion of these already combusted fuel molecules into those zones where the fuel has not yet combusted. So it depends upon two factors. First one is the heat transfer, and the second one is the diffusion. Flame propagation depends upon heat transfer between the already combusted and unburned fuel molecules, and second is the diffusion, which is the diffusion of the already burned molecules are being diffused into those zones where the fuel has not yet burned. So this is what the flow. These are the two factors on which the flame propagation depends. Moving forward, the velocity of this flame front with respect to the unburned mixture in a direction normal to its surface is called normal flame velocity. So if I draw a combustion chamber here, and this is the spark plug. Here the piston is at the top dead center. So flame will appear in this zone, and this flame will rapidly propagate throughout the combustion chamber, in throughout the combustion chamber, and this the speed of this flame, which is normal to the normal to the uh, normal to the cylinder head, or you can say normal to the piston, this speed is called normal flame velocity. So I hope it is clear to all of you that what is normal flame velocity, and this normal flame velocity depends upon the various factors, which I will explain when I will discuss the details of the flame front propagation. Uh, right now, all of you must know that what is the normal flame velocity. We will discuss the factors on which this velocity, this flame front propagation depends in the later class. So in a homogeneous mixture with an equivalence ratio e close to 1, the flame speed is normally in the order of 40 centimeter per second. So this is the normal usual flame speeds which we have when we have the fuel equivalence ratio of 1. The question is, what is equivalence ratio? I have already explained in the video tutorials of the chapter number 1 that equivalence ratio is the ratio between the actual fuel air ratio to the stoichiometric fuel air ratio. So when we have a rich air fuel mixture, this phi will be greater than 1. So it is mentioned here that when we have an equivalence ratio which is close to 1, the flame speed is in the order of 40 centimeters per second. However, in the SI engines, the maximum flame speed occurs when the equivalence ratio is in between 1.1 to 1.2. So this is the range where we can have the maximum flame speed, and the flame will rapidly propagate throughout the combustion chamber. So we can conclude it by saying that when we have a slightly richer air fuel mixture, we can have the maximum flame speeds. So and what happens if we have an equivalence ratio which is outside this operating range? If the flame is if we have an equivalence ratio which is outside the operating range, the flame speed will rapidly drop to a very lower values, and when we go beyond the operating range, equivalence ratio of beyond the operating range, then this flame will automatically extinguish, and we will not have a complete and proper combustion. So we have to ensure that the carburetor is providing the desired air fuel mixture. So now moving forward, when the flame speed drops to a very low value, the heat loss from the combustion zone becomes equal to the amount of the heat release due to the combustion, and the flame gets extinguished. This is what I explained earlier, that when the air fuel ratio, the equivalence ratio, goes beyond the operating range, so what will happen? The flame will get extinguished. So it is quite preferable that we operate our IC engine within the equivalence ratio of 1.1 to 1.2 if we want the proper combustion. Otherwise we can have improper combustion, and flame may get extinguished, and we do not have a complete combustion as a result. So however, so this is another very important factor, that by introducing a turbulence and incorporating proper air movement, the flame speeds can be increased. And this introduction of the turbulence and incorporating proper air movement depends only upon the cylinder design, the combustion chamber designing. So the designing factor here is very important. We cannot ourselves produce the turbulence inside already designed combustion chamber. We cannot do anything about introducing some additional turbulence. However, we can what we can do, if we have an IC engine which whose design is like, for example, if I have a piston in which the deflector is being incorporated, this will produce a greater turbulence, and we can have higher flame speeds in such IC engines. So turbulence can increase the flame speed, and turbulence can be increased by improving the design of the combustion chamber. So now moving forward towards the heterogeneous mixture. As I mentioned earlier, that homogeneous mixtures mean that we will have the same amount of a air fuel mixture throughout that the carburetor is preparing the same amount of a air fuel mixture, and same amount of the air fuel mixture will be going into the combustion chambers. But in heterogeneous mixture, in CI engines we basically have a heterogeneous mixture, because we are only compressing the air and fuel is being injected afterwards. So in such cases, in CI engines we do not have enough time that we prepare a proper homogeneous mixture. Rather we have a heterogeneous mixture, but that heterogeneous mixture is quite close to the homogeneous mixture. So in a heterogeneous mixture, the rate of combustion is determined by the velocity of mutual diffusion of fuel vapors and air, and the rate of chemical reaction. So the rate of combustion depends upon the two factors here, the velocity of the mutual diffusion and the rate of the chemical reaction. So what is happening in the CI engine is that we have, for example, if this is the combustion chamber, and here is the piston which is at the top dead center. This is the fuel injector. The fuel is spraying the fuel. So what will happen here is that the combustion rate here will depend upon the diffusion of these combusted. For example, the combustion at this spot has started, but the combustion here hasn't started yet. So the combustion at this point will start because of the diffusion of these already combusted particles. When they will reach here, they will provide the required amount of the energy to these air fuel, to this localized air fuel mixture. Then the fuel will self-ignite and combustion will occur at this location. So here the rate of a combustion in CI engines depend upon the diffusion of the already combusted fuel particles, and they do not depend upon the chemical reaction that much. Chemical reaction is of the minor importance. So self-ignition or spontaneous ignition of fuel-air mixture at higher temperatures develop due to higher compression ratios, and it is of a primary importance in determining the combustion characteristics. So self-ignition, as we have been studying since chapter number 1, that in CI engines only air is compressed and then fuel is injected, and that fuel will self-ignite in that hot environment of the compressed air. So the higher the temperature, the greater the chances of the combustion. So higher temperatures are developed because of the compression ratio, and this compression ratio is of the primary importance in determining in combusting the fuel in CI engines. So when mixture is heterogeneous, the combustion take place in an overall lean mixture. Since there are always local zones where equivalence ratio varies between 1.0 and 1.2, corresponding to maximum rate of chemical reactions. So in heterogeneous mixture, as I mentioned earlier, that we will have a localized combustion. We will not have the combustion in entire combustion chamber. Rather, we will have combustion in localized points, and because of the diffusion of these already combusted molecules into those zones where the fuel has not combusted, then the combustion at those points will occur. So ignition starts in this zone, and the flame produced helps to burn the fuel in the adjoining zones. As I mentioned earlier, that the combustion will start in these zones where the equivalence ratio is around 1.0 to 1.2, and then this combusted air fuel mixture will diffuse throughout the combustion chamber and will burn the adjoining zones as well. So this is what is happening in the CI engine. Similarly, in the zones where the mixture is rich, the combustion occurs because of the high temperature produced due to combustion initiated in the zones where the equivalence ratio is around 1.0 to 1.2. So in those zones where we have a very high equivalence ratio which is beyond 1.2, so because of the high temperature, the combustion will occur in those zones, and in those zones where the mixture was leaner, the diffusion is basically causing the combustion in those leaner air fuel mixture zones, and in the richer air fuel mixture zones, the heat transfer, the amount of the heat which has been released because of the combustion in these zones 1.0 to 1.2 is responsible for the combustion. Okay, now moving forward, now we have the stages of combustion in SI engine. As I mentioned that we have been studying about the working of an SI engine. What will happen that first we will have the intake stroke, then the compression stroke, then the combustion will occur, and then we have a power stroke, and then the exhaust stroke. So we are not talking about the 4 strokes here. We will only talk about from that point that where the compression has started and ended, and the combustion has begun, and then we have an expansion, power stroke. So compression to power stroke, we are only concerned with this step from compression, combustion, and then power stroke. So we will discuss these 2 strokes in quite some detail, and we will discuss the combustion in very details as well. So this is the pressure and theta diagram. Here pressure is the pressure which is inside the combustion chamber, and theta is the crank angle. Theta is crank angle, how much your crankshaft has rotated, and your piston will complete the one stroke, means that piston will move from top dead center to bottom dead center when your crankshaft has rotated 90 degree. So after when the crankshaft has rotated when the crankshaft rotates 180 degree, the piston will complete its one stroke when the crankshaft rotates 180 degree, and when it completes its one revolution, which is 360 degree, only 2 strokes will occur. Means this, for example, I'm talking about from the intake stroke. The piston is moving from top dead center to bottom dead center. Crankshaft has rotated about 180 degree. Now during the compression process, crankshaft has again rotated about 180 degree and one revolution has been completed. Now we have a power stroke, again crankshaft rotated 180 degree, and then we have an exhaust stroke. Now the crankshaft has rotated 180 degree as well. So in these 2 revolutions of the crankshaft, the cycle will be completed for 4-stroke engines. And this is what we are talking about. We are basically discussing the pressure and crank angle diagram, where the pressure is on the y-axis and crank angle is on the x-axis. Here you can see that when your crankshaft has started to move from this point A to B, here the angle was 0 degrees, and then after completing the angle of 180 degree, you can see this is the phenomena which is occurring. This is the compression process, and as a result of the compression, the pressure of this air fuel mixture, of the pressure inside the combustion chamber has increased. But you can see that this pressure increment is not that much high as compared to the pressure increment from B to C. This is the point where the combustion has occurred. Combustion has started at point B and it will propagate rapidly throughout the combustion chamber, because we are talking about SI engines, and in SI engines we have a homogeneous mixture and combustion will propagate rapidly throughout the combustion chambers. Then after the completion of combustion, exhaust expansion stroke, or you can say the power stroke, will start, and the pressure inside the combustion chamber will start decreasing again. So after completing, so this is the one 360 degree which I was talking about, compression and then the power stroke. So crankshaft has rotated only 360 degrees for now. So a theoretical pressure crank angle P theta diagram during the process compression from A to B, combustion from B to C, and expansion from C to D. In an ideal 4-stroke SI engine is shown in the following figure, which I have already explained you. Moving forward, in an ideal engine, as can be seen from the pressure theta diagram, the entire pressure rise occurs during the combustion process. I have already explained this part, that the pressure rise in the compression process is not that much not the dominant part, but the pressure rise in the during the combustion has a dominant part and has a major portion in the pressure increment. So we can just say that the increment in all the pressure has increased due to combustion, because the pressure increment due to compression is not that dominant if we compare it with the pressure increment to the combustion. However, in an actual engine this does not happen, as mentioned in the as it was shown in the diagram, that here you can see that the pressure increment is still occurring in the compression, but it is not that much dominant. So Sir Ricardo basically describes the combustion process in SI engine, and he said that it consists of 3 stages. The pressure variation due to combustion in a practical engine is shown in the figure which is presented in the next slide. So moving towards the next slide, here you can see here we have 3 different stages of the combustion in SI engine, and this is what Sir Ricardo has explained. He has basically divided this combustion in SI engines into 3 stages. Stage 1 is of ignition lag. Stage 2 is of propagation of flame. And stage 3 is of afterburning. I will discuss these 3 stages one by one. So here you can see that spark has started at the beginning of stage 1, means the combustion will start from this point, but until it reaches point B, the flame is not quite stable. The flame front is establishing and the flame is growing from A to B. It is not stable yet, but when after reaching the point B, the flame has been stabilized, and now the combustion will occur throughout the combustion chamber and it will occur rapidly. This phase is called propagation of flame, because now the flame is propagating throughout the combustion chamber. And from C to D, this is the afterburning process, means at this point the expansion stroke has started. Now the fuel molecules which are already present in the combustion chamber and not yet combusted will get combusted, or otherwise they will be released into the atmosphere in the exhaust stroke. So since the piston is moving downward, so the pressure will decrease from C to D. So these are the 3 stages of combustion in SI engine. So now coming back, in this P theta figure which I explained earlier, A is the point where the spark plug will occur, and it is, let's say, 20 degrees before top dead center. Here you can see it is shown that the 20 degree, but you can say that 18 degree, let's say 18 degrees before the spark will start, but it has not yet propagated throughout the combustion chamber. B is the point at which the beginning of pressure rise that can be detected, and you can say that 8 degrees before reaching the top dead center, and C is the point where the peak pressure has attained. So 8 degrees, for example, here you can see that 8 degrees, from 8 degree you can see the rapid pressure rise has occurred, and that is because of the propagation of the flame. Now what will happen here is that after reaching this point C, the maximum pressure has occurred. Now the expansion stroke has been started and it will move and the pressure will start decreasing. So this is what is explained in this. These are the stages of the combustion in SI engine. I will briefly go through the details. I have already explained these things. I will just briefly go through the important points and see that if any point has still remained unexplained, I will explain that point as well. So A to B was the first stage, and the name of that first stage was ignition lag, and sometimes it is also known as the growth of flame. Second stage was the propagation of flame, and the third stage was afterburning. And in the third stage, the expansion stroke has been started. So first stage A to B is referred to as the ignition lag or preparation phase, because in this phase the growth and development of the flame has been achieved, and the flame has achieved, and then in the second stage this flame will propagate throughout the combustion chamber. This is a chemical process and depends upon the following factor: the temperature and pressure, nature of the fuel, proportion of the exhaust residual gases. This is that much. This is the amount of the exhaust gases which has not been sent to the exhaust manifold because of the clearance volume. When the piston reaches the top dead center, there is this clearance volume. In that clearance volume, the exhaust gases would be there. So if the exhaust gases are higher, then the combustion, there is a possibility that these exhaust gases will offer some hindrance in the combustion process of the fresh air fuel mixture. And the next point is the relationship between the temperature and the rate of a reaction. Now the second stage was the spread or the propagation of the flame, and you can see that the rapid pressure rise has occurred in this in the second stage. So second stage is concerned with the spread of the flame throughout the combustion chamber. The starting point of this second stage is where the first measurable pressure rise has been seen in the indicator diagram. Here you can see that from A to B the pressure rise is not that much, but from B to C you can see that we have a dominant pressure rise. So this is the so from point B, from that point where the maximum where you can see that the dominant pressure rise has started to appear that is the point from where the second stage has started. So during the second stage, flame propagates practically at a constant speed, but in the first stage the flame was accelerating, and in the second stage the flame has achieved its maximum velocity and will propagate throughout the combustion chamber with a constant velocity. So heat transfer to the cylinder is lower because most of the heat energy which is being released in the combustion during the combustion will be utilized in combusting the other fuel air molecules which have not been combusted yet. The rate of heat release depends upon the turbulence intensity and the reaction rate as well. So as I mentioned earlier, that turbulence plays a very important role, and turbulence depends upon the design of the combustion chamber. The amount of the heat release, the combustion also depends upon the turbulence. If we have increased turbulence intensity, then we will have a better combustion. We will have a more rapid combustion. And the rate of the pressure rise here depends upon the amount of the heat which is being released and being utilized by the other unburned fuel air molecules, so that they can combust as well. The third stage is of the afterburning, and in this third stage we can see that the pressure has started to drop again because the expansion process has started to begin. So we can also conclude it by saying, since the pressure is dropping, so the flame velocity will also start decreasing as well, and the rate of the combustion will also be very low, and there will be no further pressure rise during this stage since the expansion stroke has already been started, and piston is moving away from the top dead center. So these are the three important stages of the combustion in SI engine. First one is the flame development or ignition lag growth and the in the ignition lag. What happens is basically the flame is growing and developing, and in the second stage, the name of the second stage is the propagation of the flame. In the second stage, that already grown flame has rapidly propagated throughout the combustion chamber. In the third stage, we have the name of the third stage is afterburning. That exhaust gases, because of the pressure rise of these exhaust gases, the piston will now start moving towards the bottom dead center, and the pressure inside the combustion chamber will start decreasing. Okay, now uh, now we have the topic of a flame front propagation. So as I mentioned earlier that I have already explained that what do we mean by a flame propagation. Flame propagation actually means that flame is rapidly growing and move, or you can say moving throughout the combustion chamber. So for efficient combustion, the rate of propagation of flame front within the cylinder is quite critical, and it depends upon the two factors: the rate of the movement of flame, and the second one is the transportation rate. So this rate of the movement of the flame is a chemical process. When we have a higher combustion rate, the flame will move rapidly throughout the combustion chamber, whereas this transportation rate is a physical process that the already combusted particles are moving throughout the combustion chamber and combusting the unburned fuel particles as well. So this transportation rate is not a dominant factor in the flame front propagation, but the combustion rate, the rate of movement of the flame plays a very vital role. So the reaction rate is the result of a purely chemical combination process in which flame eats its way into the unburned charge, whereas the transportation rate is due to the physical movement of the flame front relative to the combustion chamber walls, and is also because of the pressure difference as well. And these already burned gases are diffusing throughout the unburned gases and will force them to combust as well. So the transportation rate does not play a vital role in the SI flame front propagation of SI engine, but it depends. The major portion of this flame front propagation is of the combustion process, rate of the combustion. Now here you can see that this is the graph between the time and distance of the flame travel. So these are the two factors here, and by the word time it means that that about how much time across the combustion chamber, and so these axes are not a numerical value, rather they are in the form of a percentages. So here you can see that from stage 1 to 2, this was the first stage, which was the ignition, which was of the ignition lag, and the flame has just started to grow, and flame is basically developing. So in this stage you can see that it is taking the quite much time and has covered not that much of the distance of the combustion chamber. But after that you can see that we have suddenly we have a rapid increment in the in covering the we can say in covering the distance of the combustion chamber. And B to C is basically the second phase, and C to D is the third phase, which is of the afterburning. So again you can see that flame has just covered not that much portion, only maybe around you can say 5% of the combustion chamber, and so major portion of the combustion chamber has been covered by the flame front in the second stage, which was of the flame front propagation. So we can here we can see that in area 1, which was from A to B, the flame front progresses relatively very slow because we have a low transportation rate and low turbulence as well. And in this region of A to B, the rate of reaction is also very low, and therefore the flame is advancing. The advancement of this flame is also not that much dominant. Also, since the spark plug is to be located in quiescent layer of the gases that is close to the cylinder wall, the lack of turbulence reduces the reaction rate and hence the flame speed as well. So as I was mentioning that the flame speed in this A to B is very low, it is due to the fact that, for example, if I have drawn this combustion chamber, this is the piston, and here we have we can say the combustion, we have the spark plug. So this layer, which is quite close to the spark plug, is called quiescent layer. These layers are called quiescent layers, and the combustion in these, the rate of combustion in this quiescent layer is very low. Because of this low combustion rate, the flame speeds are very low, and when this flame goes beyond this quiescent layer into the adjoining zones, then the rapid propagation of the flame starts, and this is the section from B to C. So as the flame front leaves this quiescent zone and proceeds into more turbulent areas, that is of the area 2, where it consumes the greater mass of the mixture, and it progresses more rapidly throughout the combustion chamber at a constant rate, which is from B to C as shown in the figure. The volume of the unburned charge is very much less towards the end of the combustion. Here at point C, the volume, the unburned charge is very much less. So now again the flame travel has almost stopped, and so the transportation rate again become negligible, thereby reducing the flame speed as well. The reaction rate here is also reduced because most of the fuel has already been consumed. Therefore, in the third stage from C to D, the transportation rate are quite low. Similarly, the rate of reaction, combustion rate, is also quite low. So in stage 1 from A to B, we can say that we have low transportation rate, and because of this low transportation rate, not only that we have a low transportation rate, but we also have a low reaction rate as well, and this low reaction rate plays a very dominant role in the advancement of the fuel, and that's why the flame speeds are very low from A to B. However, from B to C, the flame has gone beyond the quiescent layer, where we have in this region we have more turbulence. Similarly, the rate of reaction is also very high. So because of this higher turbulence and higher rate of reaction, the flame here will rapidly propagate throughout the combustion chamber until it reaches the point C, where almost the entire mass of the fuel has been combusted. Some portion of the fuel is remained which will be combusted. The pressure has start decreasing, and the flame speed has also start decreasing because the rate of the reaction and the transportation rate has also started decreasing. Rate of the reaction is decreasing because we have very small molecules of the fuel which is being left for the combustion. Now next we have some factors which basically influence the flame speed. First one is the turbulence. So I have already mentioned that higher the turbulence, it will result in the higher flame speeds, because what is turbulence? Turbulence is basically the physical intermingling of the burned and unburned fuel particles, and the unburned fuel particles will take the heat from the burned fuel particles and will also get combusted. So this is what the turbulence this is what the role of the turbulence here is. So increasing the turbulence will increase the flame speed, and reducing the turbulence will decrease the flame speed. However, so another factor here which needs to be understood is that how much turbulence is required. For example, if we have a very high turbulence, then it will not help in propagating, in developing the flame, rather it will extinguish the flame and will produce a rough and a noisy operation as well. It is just like the fact that when the higher wind is blowing, it will not help the flame to grow, and so the increased in turbulence will basically extinguish that flame which is still developing, which is still in the development phase and has not fully developed. So turbulence should be high, but it should not be that much high. Particularly in the quiescent layer, we have low. It is desirable that we have a low turbulence in the quiescent layer. Next is the fuel air ratio. So as I mentioned earlier, that for the equivalence ratio of 1.1 to 1.2 for SI engines, we have a maximum flame speed, and as it can be seen from this figure as well, that from the equivalence ratio from this point until this point. Okay, on the x-axis you can see this is 60 and this is 100. So it is given in the percentage form. If I write it in the equivalence ratio form, it will be 0.6 and this one will be 1.0 and this point will be 1.1, and here this is 1.2. So from this, at this point we can see the flame front propagation is taking very less time. It means that it is covering the larger distance in smaller time duration. So it means that we have a maximum speed from point A, or we can say from 1.1 to 1.2 equivalence ratio. But when we increase the equivalence ratio beyond that, the flame, it will take greater time and the speed of the flame has started decreasing. So the higher flame speed is obtained when we have somewhat a rich air fuel mixture, and as I mentioned earlier that this 1.1 to 1.2 is a rich air fuel mixture. I have already explained this part. I will again mention here that Here you can see equivalence ratio is the ratio between the actual fuel air ratio to the stoichiometric fuel air ratio, and when we have the equivalence ratio of 1, we will have a rich air fuel mixture. I have already concluded this point here. When the mixture is slightly richer than the stoichiometric, so we can have the equivalence ratio of 1.1 to 1.2. Now coming back, next factor is of the compression ratio. As I mentioned earlier, that the higher compression ratios will increase the pressure, will increase the operating pressure and temperatures of the working fluid and your IC engine, which will result in the higher flame speeds. So by increasing the pressure, by increasing the compression ratio, pressure and temperature of the working fluid has increased, which will result in increment in the flame speeds as well. Next is the temperature and pressure. By increasing the compression ratio, the temperature and pressure, operating temperature and pressure of the engine has been increased, so the flame speed will increase. And these higher temperatures and pressure will result in the preparation of a better homogeneous mixture as well. So the better the more the homogeneous mixture, the more it will help in the increment of the flame speed. Next is the engine output. When we increase the engine output, we are basically operating our IC engine at the higher pressures, and since we are operating at the higher pressure, the flame speed will also increase. Next is the engine speed. Engine speed increases the flame speed almost linearly, because engine is operating at the higher speeds and the piston is moving more rapidly. So because of this movement of the more rapid movement of the piston, we will have the increased turbulence, and increment in this turbulence will result in the higher flame speeds. Next is the engine size. The size of the engine does not affect the flame front propagation, and the only thing is the flame is propagating with the same speed. Since the size of the combustion chamber is very large, therefore it will take much more time to cover the entire combustion chamber. So that's why the bigger IC engines usually operate at the low RPMs, and the smaller size engines operate at the higher RPMs. Okay, next is the phenomena of knocking, and as as we have already studied that knocking is undesirable. So now we will discuss that how these knocking basically occurs in the SI engine. In SI engine, I have already explained in the previous topic. It has already been explained that knocking is undesirable, and it usually happens when the fuel air mixture inside the combustion chamber self ignites, which will produce an undesirable audible sound, and it is called knocking, and it can also have some drastic effects on your IC engine as well. So in IC engine, combustion is initiated with the flame produced by the spark plug. The flame which separates the burned part of the mixture from the unburned part propagates into the combustion chamber. This is still we are talking about the combustion in the combustion chamber. Because of this propagation of the flame, because of the combustion of these fuel air molecules, large amount of the energy is being released, and there is an increment in the pressure and the temperature of the burnt part of the fuel air mixture. So what will happen here is, if I divide the fuel air mixture in the combustion chamber into some layers, here you can see that this is the combusted part. For example, the temperature of this combusted gases they will have a higher temperature, they will have a higher pressure, and since they are at the higher temperature, they would be transferring some heat in the adjacent layer of the fuel air mixture, which is still not yet burned. It is transferring the heat energy in the next layer. And then let's say the combustion occurs, the normal combustion occurs in the second layer as well. Now this layer will compress the next layer, and not only it will compress, but it will also transfer the heat, since this layer is at higher temperature. So two factors are occurring here. It is compressing the layer which is after the burnt layer, and it is also transferring the heat as well, because the combusted layer is at the higher temperature. So what will happen? So at some point, when we are talking about the abnormal combustion, when we are talking about the knocking, at some point in any layer, what will happen? For example, at this layer, what will happen is that if the temperature in this layer reaches, or we can say goes beyond the self-ignition temperature of the fuel, another flame will appear. The self-ignition in this layer will occur, and the second flame will be produced, and this flame will propagate in the opposite direction from where the flame of the combustion is coming. In the second layer, in the layer which is after let's say towards the end of the combustion chamber, we will have at this layer, in the temperature has exceeded the self-ignition temperature, so another flame will be produced, and it will move against the main flame which is coming from which has been produced by the spark plug. So this phenomena will produce an audible sound, and this phenomena is called knocking in SI engine. So the knocking in SI engine is occurring almost at the end of the combustion. So again, moving back, I will just complete this part, that the burnt part of the mixture will expand, and it will compress the unburned part, the afterward layers, thereby increasing its temperature and pressure. And if this temperature and pressure goes beyond the self-ignition temperature, another flame will be produced in that unburned layer, and it will move against the main flame, and audible sound would be produced, which is known as knocking. If the temperature of the unburned mixture exceeds the self-ignition temperature of the fuel, the spontaneous ignition or auto ignition occurs at various points. This phenomena is called knocking. So when we are talking about the normal combustion, there will be no self-ignition in any of the layers inside the combustion chamber, and the combustion phenomena will take place just like this. But when we are talking about the abnormal combustion or knocking, then let's say this is the layer in which the normal combustion is occurring, but in the second layer the temperature has exceeded because of the compression from the first layer and the heat transfer from the first layer. The temperature has exceeded the self-ignition temperature and another flame has been produced in this layer. So knocking will occur at this point, and here you can see that we have a pressure pulses at almost at the end of the combustion stroke. So in the abnormal or knocking combustion, the temperature of the unburned charge had reached its self-ignition temperature, and this charge will auto-ignite, which will lead to the knocking combustion. Because of the auto-ignition, another flame front starts traveling in the opposite direction to the main flame front, and when the two flame fronts collide, a severe pressure pulses are being generated. So we can conclude it by saying, in order to avoid the another thing that I want to mention here is the combustion, the knocking in SI engine is also referred as detonations, because its sound is just like some detonators, and it has a very drastic effect on the IC engine. So in order to avoid the detonation, or you can say knocking, a high auto ignition temperature of the fuel are desirable. High auto ignition temperature means that the fuel should have a longer ignition lag, means it requires more time to burn the flame front through the unburned fuel air mixture. So it has to, we have to ensure that we uses the fuel which has a higher auto ignition temperature, or you can say, we can say that it should have a longer ignition lag. So the impact of knocking on the engine component and structure can cause engine failure, and in addition the noise from the engine vibration is also very objectionable. So we have to ensure that we do not have any sort of a knocking in the IC engines, in our SI engines, and we can avoid that knocking by utilizing a good quality fuel which should have a higher auto ignition temperature, or should have a long ignition lag. Next is the different factors on which the knocking depends. I think I should end this video lecture here. I will start off the different variables which depends on which the knocking depends in the next video tutorial. So make sure you go through this video very carefully and understand the concepts of the combustion in SI engine and the knocking in SI engine. And in case you have any sort of a query, any sort of a question, you can just note down your question and you can ask me the question in the online sessions, or maybe through the WhatsApp group or the video or the Google class as well. So till the next video, Allah Hafiz.